Hi grade 12s. Basically we are moving on to a new topic within calculus. So what happens within calculus is there's a number of units that we cover. And the first unit that we covered was differentiation. And so we did a whole bunch of different differentiation rules and different functions that we differentiate, which was kind of all one unit. Now we're moving on to a second unit, which is where we apply these derivatives. So how do these derivatives help us? And there's a couple of topics within this big unit. So I've written the heading Applications of Derivatives, and there's going to be a couple of topics under this heading. There's also another unit within calculus, which we will eventually get to, which is integration, and we'll get there in due course. Now this video should be a complete summary and revision of what we learnt in grade 12 normal calculus. So that's why I've typed out these notes, because they should be things that we just have to remind ourselves so that we can move on to the more difficult stuff. So let's just have a look at topic 1, which is the summary of derivatives. So f dash x is greater than 0. That's the first thing that we should know. Remember, f dash means gradient. We know that. Now, if f dash 0 is greater than 0, it means the graph is increasing, because basically the gradient is positive. Now, this is a new kind of terminology for us. Increasing graphs can be constant or increasing. So, for example, if you had a graph which looked like that, you would call that an increasing graph, even though it has a stationary kind of point in the middle. Technically, if you use the word strictly increasing, that means you never have a constant bit and it's always going up. Now, those aren't particularly tested words or anything, but just some technical words for us. Okay, let's look at the next one. F dash x, so the gradient is negative, means the graph is decreasing, and as we said with increasing, decreasing graphs could be decreasing or constant, and they would still be considered a decreasing graph. So for example, the cubic graph, which does that, even though it's stationary at one point, we would say that that graph is decreasing for all values of x, even though there is a point where it's stationary. Strictly decreasing means that you are always decreasing and you're never constant. So this particular cubic graph, I would argue, is decreasing for all values of x, but I would say it wasn't strictly decreasing for all values of x. Okay, then something else we definitely know is that your derivative, your gradient, is 0 at a stationary point. So that's going to be really important for us when we start drawing graphs. Right, a new word for us, a monotonic increasing function, means the entire graph never remains constant nor decreases, but increases the entire time. So for example, a straight line going up would be a monotonically increasing function. A parabola, however, would not be, because it was decreasing and stationary. The cubic graph that looks like that and has a stationary point would not be monotonically increasing, because it is stationary at a point. A monotonic decreasing function is exactly the opposite, and that means in the entire graph never is constant nor increases, but decreases the entire time. So easiest example to think of would be a straight line. Another kind of easy example would be an exponential. An exponential, if you had a base which was less than 1, that would be a monotonically decreasing function. So yeah, those are just some nice fancy words. Then concavity is going to be really important for us in AP Maths. In normal maths we kind of touch on the idea, but in AP Maths this is very important. So don't forget that when your second derivative is positive, you have a graph which is concave up. So it's concavity, it's shape. Now just to draw concave up, we are going to do these in notes that are still to come. That would be concave up. Concave down is exactly the opposite. So if the second derivative is negative, it's concave down, and I will explain that in a second. And then lastly, something we should know, if the second derivative is 0, it could mean a point of inflection. Now, in normal maths, most people teach that to find a point of inflection, second derivative is 0, you have a point of inflection. And the reason why you can assume that in normal maths is that we only do cubic functions. And in a cubic function, where the second derivative is 0 is always a point of inflection. However, that's not true in all functions. And so really, really importantly, if your second derivative is 0, it might be a point of inflection, but it also might not. So it's never in AP Maths, and it shouldn't be in Maths as well. It's not going to be acceptable to just find the second derivative and set it equal to 0, because that answer that you get doesn't have to be a point of inflection. Now we're going to go into more detail with points of inflection and concavity and how to find them in a video in a couple of lessons time. So this is just a brief recap. Now I've drawn a cubic graph here just so that we can label in a brief revision of what we should know. So first of all, there's my stationary points. So that's where my first derivative is 0, and that's where my first derivative is 0. So there's 2 stationary points here. This part of the graph here will be where your gradient is positive because the graph is going up. So my gradient is positive. However, if you look at the gradient, what's happening to the gradient? As I travel up, my gradient is getting shallower and shallower and smaller and smaller and smaller and smaller until eventually it's 0. So what's happening there is my gradient is decreasing. Yes, my graph is increasing, but my gradient is decreasing. Now don't get confused with the fact that my derivative is positive. The graph is going up, but the gradient is decreasing. So the gradient is going down, and therefore my second derivative is negative. And that's why in this part here, that would be called concave down. Now what's happening in this part of the graph here? Now there will be some point in the middle here of this. Now that doesn't look like the middle, so let's make it a little bit more realistic. There'll be, oh, that looks terrible. Let's try this again. There'll be some point round about the middle here where your graph changes concavity. So what's happening here, let's just note, this gradient is negative because my graph is going down. But my gradient is still decreasing because if I drew a whole bunch of tangents, my tangents are getting steeper and steeper and steeper. So yes, my gradient is negative, but my gradient is also decreasing because my gradient is getting more and more negative and steeper and steeper and steeper. Now that means my second derivative is still negative. So this entire time, up until there, my second derivative is negative. So notice that your gradient can change sign. So your derivative changed sign here, but my second derivative did not. Now this point here is where my concavity changes. So this entire part here where my gradient is, my second derivative is negative, is called concave down. So this entire shape is called a concave down shape. Now what happens after this point of inflection is that part of the graph. Now in this part of the graph, my gradient is still negative. My graph is going down. However, if I drew in a whole bunch of tangents to kind of look what's happening, the gradient itself is now increasing because my gradient is going from a steep negative to a shallow negative and then eventually to 0. So if my gradient is increasing, my second derivative is now positive, and that's why it's called concave up there. So this point here is my point of inflection. If I know it's a point of inflection, that means my second derivative is 0. If I don't know it's a point of inflection, then you could find the second derivative being 0 and it's not necessarily a point of inflection. But at a point of inflection, your second derivative is 0. Now that point of inflection is when your concavity changes. We will be making more notes on this in future, so this is just a brief summary. Now what happens in the last part of this graph is, let me rather use this color, is now the graph is going up again. So in this part, yes, my gradient is now positive. So my gradient has changed sign. In the green section, it was negative. In the light purple section, it is now positive. So my gradient has changed sign. And my gradient is now increasing because the graph is getting steeper and steeper and steeper. So if my gradient is increasing, my second derivative is now positive. So that means that this entire time, maybe I should use a different color, so maybe let's use this one. This entire time, my second derivative was positive. Therefore, I am concave up in shape. So it's quite confusing because your gradient can change sign, but your second derivative doesn't. So just to note that again, that's where my gradient changes sign. And yet this entire time my second derivative was negative. So even though my first derivative changed sign, my second derivative did not. Again, my first derivative changed sign, oh that's a terrible drawing, but anyway, changes sign at that stationary point, but my second derivative is positive that entire time. So where does the second derivative change sign? At my point of inflection. Okay, now again, we are going to come back to this idea when we start drawing functions, and we'll dive a little bit more in depth, but this should have been what you discovered in grade 12 normal maths. So let's just look at a couple of examples to make sure we know what we're doing when it comes to gradients. So first question says, consider the function x to the power of 4, so this is the power of 4 equation, and it continues. Determine the values of x for which the function is increasing, decreasing, and stationary. Now all of these are about the first derivative. So I'm going to say, right, what is my first derivative? If I differentiate, I bring down my 4, but it cancels. So bring down the 4, but it cancels. Minus 3x squared minus 4x plus 12. Now, all of this is going to depend on the sign of the gradient. So I'm going to draw myself a number line. Most importantly, please remember that this is AP Maths. So we absolutely do not solve equations manually. We pick up our calculator and we use the equation function. Please don't show any factorizing. That's not what this is about, and so it's a waste of time. So if I just use my calculator, I get values of -2, where I will have a intercept. I get 3 and I get 2. So let me make this 2. And then we make this 3. Now, multiple ways to do this question. You could draw this as a cubic, because this is a cubic, and this cubic has a positive value there, which means the graph will go up, it'll turn, it'll go down, and it'll go up again. So you could draw yourself a cubic, very similar to how we draw the parabola when we're solving inequalities. Or you could substitute in any value less than -2 into the cubic. So substitute in any value less than -2, well, that doesn't have an x, and basically work out the value of f at that point. And you will get a negative there. These are 0. And then you should know that unless there's multiple factors that square, it basically changes sign. So it's negative, positive, negative, positive. So either do the blue version where you actually draw in the cubic, or you can do a number line with the signs. Now this question said, let's go back to A, it says where's the graph increasing? So that means I want the gradient to be positive. Now technically it says increasing, and if we go back to our notes, technically increasing means the graph can be constant or increasing. So you could actually include where the gradient is 0. So technically you could do that. I would personally accept both. So how do I get my answers here? Well, where is it positive? So x is between -2 and 2, or x is greater than 3. I can see that by the signs. Now, just be a little bit careful. I think what people might get confused about is, oh my word, look at this cubic isn't increasing the whole time there, But careful, this is a picture of the gradient, and the gradient is positive there. So actually, I think what might be more helpful is not to look at the cubic, but to look at the signs. I often use the cubic to get me the signs, and then I always look at the signs. So where is the gradient positive? In those regions. You could, I skipped out a sign here, so let me go put it in. I could include these points technically. Based on the technical definition of increasing, I could use that, but we will mark both correct. Personally, when you say increasing, I can't include stationary. It just doesn't sit right with me. So question B, where they're negative, well, that's where your derivative is less than, or you could say equal to 0. So that would be x is less than minus 2, or that would be the x's between 2 and 3. Again, if you chose to include those values, they would mark it right. When it is at stationary, let me choose blue. When is it stationary? It's stationary when your derivative equals 0. And that's at negative 2, at 2, and at 3. Great. So hopefully that's a good reminder of differentiation, increasing, decreasing, stationary points. Okay, let's have a look at another one. Prove that f of x equals 5 over x cubed is monotonically decreasing. Now, monotonically decreasing means my derivative must be negative, not equal to 0, negative the whole time. So let's go find f dash of x. Well, before I find f dash of x, it might be helpful for me to rather write this as an easier differentiable function, which looks like that. Now it's easier to say, great, this is negative 15, x negative 4, and I'm going to go even further, and I'm going to write it like that. Now I need to prove, now just be careful, when we say prove, we like to write things out mathematically. Prove this is monotonically decreasing. So I would then say, well, therefore, x to the power of 4 is greater than or equal to 0 for all x values. Because when you raise something to the power of 4, it's always positive. That means if you have negative 15 over x to the power of 4, that will actually be less than 0. Now, I'm not saying equal to 0. Now, why am I not saying equal to 0? Well, x can't be 0 because it's in a denominator. So the top is negative 15 and the bottom is a positive number, but it can't be 0. And so actually this is technically always less than 0 for all x is an element of reals, or x for x is not equal to, sorry, let me say that again. So this derivative is always less than 0 for all x is an element of reals, but x is not equal to 0. Now you might say, oh, but then if x is 0, then the graph might be stationary. But just be careful. This particular function, f of x equals 5 over x cubed, has a domain which is x is an element of reals, but x is not equal to 0. Why? Because x is equal to 0 would be a vertical asymptote, because you can't divide by 0 here. So this graph isn't defined at 0. And so for all the points that it is defined at, its gradient would be negative, because you would have negative 15 divided by something which is always positive. And a negative divided by positive will always be negative. So the only reason I don't have to worry about this 0 is that it's actually not part of the graph. It's an asymptote. So at every single x where this graph is defined in the domain, this gradient would be negative. So it's monotonically decreasing. So I probably would insert a line here that said, therefore, f dashed. Now, if I look up here, I think I wrote f dash dash, which is terrible. So let me just erase this up top here. I think up top here, for some reason, who knows, tiredness, I wrote f dash there, or maybe it was a slip. So going back here, I would say, therefore, f dashed of x is equal to 0 for all x is an element of reals, but x is not equal to 0. So this is always going down. Okay, example 3. Oh, very similar question to what we've done before. Determine the values of x for which that function is increasing, decreasing, or stationary. Now, why do we want to be able to find these out? Well, in a couple of lessons time we're going to be drawing that function, and you probably have no idea what that function currently looks like, and we need to know. So finding out where it's going up and down and stationary is really important to us. So let's have a look at y dash. Now this is a quotient rule, and the quotient rule says differentiate the top, so that's 6, leave the bottom, so that's x squared minus 3, minus, leave the top, multiply by the derivative of the bottom, which is 2x, all divided by x squared minus 3 squared. So if I simplify this a bit, I get 6x squared minus 18 minus 12x squared plus 24x all over this. Now we never multiply the denominator, because if this has any hope of simplifying, you would need to keep that factorized. So this is negative 6x squared plus 24x minus 18 all over my denominator squared. Now this seems horrible to work with, but it's not really a problem, because in question A, for increasing, I would need y dashed to be greater than or equal to 0, or just greater than. It doesn't really matter. Now that's actually really easy, because that means that negative 6x squared plus 24x minus 18 all over this denominator has to be greater than or equal to 0. But this is positive. So this is greater than or equal to 0 for all x is an element of reals. And so I don't have to worry about that. So what this means is, therefore, I'm looking where negative x squared plus 24x minus 18 is also positive. Because if this is positive, so that's positive. I don't know if I said negative or positive just now. That's positive because it's being squared, so the top has to be positive. So basically, I'm solving an inequality just based on the numerator. Now for the next question, where is it decreasing? This is going to be exactly the same argument. That denominator is always positive, so it doesn't play a role at all. When is the graph stationary? Well, that denominator can't equal 0, so this denominator is never playing a role, and all of these answers are going to depend on the numerator. Now that's a parabolic inequality. How do I want to solve it? Well, there's multiple options here. I could do a number line. I probably would keep the numerator as it is, even though it can simplify, because I've got a calculator. So I'm just going to draw a number line and then probably just put in values. So when I use my calculator on the equation mode, I got 1 and 3, and that's where the numerator would equal 0. So immediately I know where the stationary points are. They're at 1 and 3. Now I substituted in a value less than 1, and I got a negative sign, and then I substitute, and obviously I should know that in a parabola it'll change signs. There's no repeated factors, and it'll change sign. So now I can answer all these questions. So in question A, when is the gradient greater than or equal to 0? Well, the answer is going to be, well, it must be between 3 and 1. You can include those technically with the use of increasing, that word. When is the graph decreasing? Well, for x is less than 1, or x is greater than 3, so that's technically could be equal to. When is it stationary? Well, x is equal to 1, or x is equal to 3. So when we start drawing these types of functions, this skill will be very useful to us, because we know where the graph is going up, we know the stationary points, so we can start figuring out the shape, because these aren't just stereotypical graphs that we're used to. Right, next question. Example number 4 says, show that g of x is equal to negative 2 ln 5x plus 2 is decreasing for all x is greater than negative 2/5. Okay, decreasing would mean my, in this case, g, my derivative would have to be less than, or it could be equal to 0 technically, which means I need a derivative. Now this is going back to the derivative of ln's. That's quite fun. Okay, now negative 2 is just a coefficient, so it's negative 2. Now the derivative of ln is 1 over what's inside the ln, but careful, what's inside the ln, this is a chain rule. So ln is the outside function, so it's 1 over the inside function, but now I must times by the derivative of the inside. And the derivative of 5x plus 2 is 5. So this becomes negative 10 over 5x plus 2. Now, we're trying to show that it's decreasing. So my derivative would have to be less than equal to 0. So therefore, negative 10 over 5x plus 2 would have to be, now I'm going to say less than 0 and not equal to 0, and I'll tell you why. This can never equal 0, because negative 10 is the numerator. The denominator can't possibly equal 0. It's not allowed to be, and negative 10 isn't 0. So this gradient can never equal 0. So basically I'm finding out when is negative 10 over 5x plus 2 less than 0. Now, if this is negative, so negative 10 is less than 0. So that means your denominator has to be a positive, because a negative divided by a positive will get me a negative. So because my numerator is negative, my denominator needs to be positive. So that means that 5x must be greater than negative 2, not equal to, because my denominator is not allowed to equal 0. And so x must be greater than negative 2 over 5, which is exactly what that says. That's just interval notation. Don't forget the round bracket means from, but not including. So from negative 2/5, but not including negative 2/5, up to infinity. And you can't include infinity because it doesn't exist. Right, moving on to our last example. Show that h of x, which is equal to root x, has no stationary points. Well, stationary points are around the first derivative equaling 0. So first of all, let me go write h of x as x to the power of a half. So what is my first derivative? Well, I would bring down my exponent and subtract 1. So when would this equal 0? Well, we'd have 1 over 2, and this would be root x at the bottom. Now, this is going to have no solution, because if I try and multiply by 2 root x on both sides to solve this equation, so if I multiply by 2 root x on this side and I multiply by 2 root x on this side, these cancel, but I get 0 equals 1, which is not possible. Therefore, there is no solution. Another way to think of it logically is to go back to this line here when you say 0 equals 1 over 2 root x, and to argue if this 1 isn't equal to 0 and this is not allowed to equal 0 because it's the denominator, there's no ways you could divide here to get 0. Don't forget that the only way to divide to get 0 is if your numerator is 0, because your denominator is not allowed to be. So either way, there's absolutely no solution here, which means there are no stationary points. So I'm going to say, therefore, h dash x cannot equal to 0, therefore no stationary points. Great, so hopefully that was just a brief recap. We will go into this in more depth when we start drawing these cool functions, but just a brief recap on stationary points, gradients, points of inflection. Well done.